This is a lecture on using unlearned neural networks as image priors for inverse problems. And in this case, an unlearned neural net means a neural network that has never seen training data nor has been officially trained. It's really just a collection of random weights ready to solve an inverse problem of interest. All right, so what are these problems? Well, we'll consider problems from imaging. So let's let X be an image, which is in Rn, so it has n degrees of freedom. And let's let y be the observations of this image. We'll assume we have m of those, and so this lives in Rm. There's going to be some forward model or degradation model, capital F, and this is going to be a map from Rn to Rm. There's going to be some noise, which we'll call eta, and so our observations are y equals capital F of x plus eta. The inverse problem is given f and given y, find x. We've seen a couple of examples of these problems, but some are, if f is the identity, then this problem would be called denoising. If f is a subset of the rows of the identity matrix, then this would be an in-painting problem, where you're filling in missing pixels of an image. And if f is a random matrix that's m by n, where m is less than n, then we might call this compressive sensing. Now, to solve inverse problems using neural networks, we've seen a couple of varieties of these. So let's review some of those. First, we saw end-to-end nets. And in these cases, they went as follows. We chose an architecture, some f theta, which mapped from Rm to Rn. We then had a training phase, where we either collected or created a data set, which consisted of pairs, xi and yi, of images and their degradations. So this data set could either be collected from in the wild or perhaps synthetically generated if you have an accurate model of your forward process. Then learning was done in order to estimate theta such that xi is roughly some f theta of yi. And here f theta is some neural network with parameters theta. Now, once this model has been trained, then at inversion time, it's a relatively straightforward process. Given y, compute x equals f theta of y. So this system was trained in an end-to-end manner. In inversion time, it's straightforward. We also talked about another approach of generative modeling. So this approach involved beginning by choosing an architecture, which in this case we'll call g of theta, and this is a map from Rk to Rn, where k is some latent dimensional space, or some latent space of low dimensionality. There's going to be a training phase here as well, which begins by first collecting a data set of xi's. So these are the images that you're trying to, that are of the class that you're trying to recover. So after you've collected that data set, then you want to learn theta such that g theta of z for standard normal z approximates the density from which the data set was sampled. And examples of this process are variational autoencoders and generative adversarial networks, just to name two. Now at inversion time, then we're given a y, and we already have our g theta, so our goal is to find a z such that capital F of g theta of z is roughly equal to y. We do this by solving a minimization problem. Now we want to contrast these to unlearned neural network priors. In this case, we begin the same by choosing an architecture. In this case, some f theta, which will be a map from Rk to Rn, for some value of k. There's going to be no training phase, which means that we don't have to go collect training samples that are similar to the natural signal class we're trying to model. And then in inversion, then we begin by fixing some z, which is going to be the input to f theta. This is going to be fixed and is going to be independent of the image that is trying to be recovered. Now, given measurements y, the goal is to find theta such that capital F of f theta of z is roughly equal to y. And this will be done in an optimization sense as well. So the big difference from before is that here the parameters of the neural network are optimized at inversion time instead of at training time because there's no training. So let's see exactly what this comparison is. Right, so here, let's compare generative models and unlearned priors. Right, so they both have a neural network, which is going to take two inputs, z and theta, and it's going to output an image x, which is fed through a forward model, which is combined with noise eta in order to get measurements y. So in the generative model case, theta is learned from data, and it is general to all images. So then the z is fit to a particular measurement, and it's specific to a single image. Now with unlearned priors, it's basically the opposite. Here z is fixed and it's general to all images, and theta is fit to measurements for a specific image. All right, so we come to a very interesting question, which is, can a neural network with no training data at all be a good prior for inverse problems? And the answer here, perhaps surprisingly, is yes. And what this means is that the architecture itself of the neural network has bias towards some images or signals over others, and it exploits that bias in the inversion process. The rest of this lecture is going to talk about 3 papers in detail: the deep image prior, the deep decoder, and the deep geometric prior. And all 3 of these papers, their information is in the description below this video. After we talk about these 3 types of priors, then we're going to show that unlearned priors can also aid learned priors. And these ideas are in 2 additional papers, the image adaptive GAN and the latent convolutional models paper, both of which the links are in the description below. All right, let's begin with the deep image prior. The deep image prior is an untrained neural network whose weights can be optimized in order to fit measurements. Right? So it's a neural net, so we can talk about its architecture. And this net is going to have an encoder-decoder architecture, which is going to follow a U-net. So there's going to be some input z, which remember is, say, random noise, like sampled once. Then there's going to be a whole bunch of downsampling layers, followed by a whole bunch of upsampling layers, and then skip connections at corresponding levels. And in the downsampling and the upsampling, the output is going to be an image of the same dimensionality as what we're trying to recover. Now, all of the downsampling layers are going to have this structure where the image that comes in is going to have a convolution, a downsampling, normalization, and then a ReLU. And then they're going to have another convolution, downsampling, batch normalization, and ReLU. And this is going to repeat. And in the decoder part of this architecture, there's going to be a upsampling operation in addition to convolution and batch normalization and ReLUs. So the architecture of this is has a lot of knobs. All of these convolutions have a filter size. All of the connections here can be learned. There are a lot of parameters that are estimated at inversion time. Right, so this is the architecture of the deep image prior. And what is interesting is that the deep image prior can represent all images, but it has a high impedance to noise and a low impedance to signal. And this is going to be one of the key things that makes it work. So this is a figure from the deep image prior paper, and this is an illustration. Given a single image, then solve this minimization problem. So minimize over the parameters theta of the network of the norm of f theta of z minus x. And what's being plotted is the mean squared error of the recovery versus the iteration in a logarithmic scale. And the curves here involve fitting an image with noise, an image whose pixels have been randomly shuffled, and then just an image consisting of nothing but noise. Right? And so what we can see in then all of these cases is if you run the optimization long enough, then you can fit noise. Right? This is because the neural network is highly overparameterized. It has a lot of capacity. But we also observe that it takes a lot of iterations in order to fit the noise. And it doesn't take as many iterations to fit the signal. So we see that yes, it can fit noise, but it doesn't until after the signal is fit. And according to this figure, by about 1 or 2 orders of magnitude of iteration count afterwards. So what this suggests is that there is a high impedance to noise, right? It takes a lot of iterations to fit the noise, and a low impedance to signal. And so perhaps you can denoise by doing early stopping. And indeed, they see that this is the case. So they see the deep image prior with early stopping can denoise an image. So what we're seeing here, the leftmost image is an image which has JPEG artifacts. So if you zoom in close enough to this image, you can see these sort of blobs that appear that are not part of the intention of the image. So then each frame shows the output of the learned or of the estimated model at various number of iterations. And we see that initially, if there's too few iterations that have occurred, then we get a blobby representation of this image. And then eventually it starts looking like the real image. At some point, it seems to fit the image really well. And then if the optimization is allowed to continue after that, then it overfits the image, and in particular fits the noise, in this case the JPEG artifacts, that we wanted to remove. So here we visually see that we can fit any noisy image, but we do in fact fit a clean version of that image first, even in this vector graphic type situation. So the geometric picture of what's going on with the deep image prior is as follows. So we have some noisy image which we're trying to recover. There's some set of clean natural images that exist, and then there's going to be some initialization that was random, where there's an image that's the output of a purely random neural network, and that's not going to be a clean natural image. So as we optimize the weights of this neural network toward the image given, then it seems that it first goes into this region of clean natural images, and then eventually starts overfitting to the noise, and then leaves that region to fit the noisy image itself. And this is the basis of saying if we did early stopping, then you could get the clean natural image that's quite close to the noisy image that you want. So there are other things that deep image prior can do. For example, it can do super resolution and some inpainting. So here, these are, again, figures from the DIP paper. The left figure on top shows an image of a butterfly. If you downsample it by 4x and then bicubically upsample it, you get this image in the middle, which is blurry. If instead you use the deep image prior at the same 4x upsampling, you get much crisper edges. And so we see this very nice property that the deep image prior somehow already knows that crisp edges are nice, already knows that there are continuity properties within natural images, and it outputs a higher quality image than this bicubic upsampling itself. The DIP could also be used for inpainting, and here's an example of that, where there's a picture of a room with a vase missing, and then the DIP was asked to fill in that vase, and indeed it does a pretty good job and fills in the railing that's behind this table in the image in a credible visual way. And so these are quite interesting because let's remember that these methods never saw training data. Right? They've never seen natural images before. They didn't learn anything. They only fit the measurements that they had via a neural network of this UNet architecture. We could ask, two questions. Right? So here's another inpainting problem, or here's two images of people's faces with some pixels removed, just like in the previous case where the vase was removed from a table. And a question that you can ponder is, could the deep image prior in-paint these images well? Now, another question you could ponder is, if you're doing compressed sensing, would the deep image prior need early stopping? And I'll leave these questions for the viewer, you, to think about. And if you're so inclined, please write in the comments below what your thoughts are. So now we're going to talk about the deep decoder. Right? The deep decoder is very similar to the deep image prior, but it has an architectural simplification. And primarily, it is only the decoder part of the deep image prior. So one of the interesting things about the deep decoder is that it can be underparameterized. And by that, what I mean is that the number of neural network weights is less than the number of pixels in the image. So this is not usually the regime in which neural networks operate. Typically, almost all neural networks that are useful in practice are highly overparameterized. But with a deep decoder, you can actually be underparameterized. Now, what this enables is concise image representation, leading to the possibility for image compression. It also enables a method that doesn't need early stopping. And what that means is that the architecture itself contains all of the prior about the natural images, that it's not part of the algorithmic process of early stopping. Also, in this underparameterized model, it admits some theory about how the deep decoder can't fit noise. While some deep decoders can be underparameterized, it's also possible to have overparameterized variants, and these can be particularly effective for compressed sensing, but we won't discuss those now. So the deep decoder architecture is as follows. It's going to be a neural network, as before, which takes some input and has an output, which is a color image. Right? So the input is going to have correspond to a smaller image, but with k channels. Then there's going to be a series of layers where the size of each layer doubles through some upsampling operation, and there are additionally ReLU terms, channel normalization, and some one-by-one convolutions. And so if you chain these together, then we get a deep decoder. So to zoom into this architecture, we're going to have some input, which we used to call Z, but now we'll call B0. It should be thought of as a matrix, right? For each incoming pixel, there's going to be k channels that are values corresponding to that pixel. Now, the operations are going to be as follows. First, there's going to be an operation of linear combinations of the channels within a pixel. And this is going to be translationally and variantly applied to all pixels. Now, alternatively put, a one-by-one convolution is taken. And this can be represented by a matrix Ci minus 1 if it's acting on the matrix Bi minus 1. So after a one-by-one convolution, then what's going to happen is that activation map is going to be upsampled using some fixed upsampling operator, which we'll call Ui minus 1. Then after the upsampling, which may double the image in size or scale by some other factor, then a ReLU is going to be applied, and then some channel-wise normalization is going to be applied. And this is going to get us the output of this layer, which we'll call Bi. So here, there are two quantities that are optimized over. One is the matrix C, which corresponds to the one-by-one convolution, and also the normalization parameters, the gamma and epsilon that appear just like in batch normalization, except they're being applied over channels. And so in this architecture, typically the number of channels is kept constant in each of the layers, so let's call that K. And so then the matrices C are K by K matrices. Now, if that's the case, then after D layers, then the output is also going to have K channels, and so the final layer of the deep decoder is going to map a a map with k output channels to one of 3 output channels, and this is just going to be given by a 1-by-1 convolution with 3 output channels. Right? So mathematically, the deep decoder will have the structure where the I plus first value of matrix B is going to be the channel-wise normalization of the ReLU of the upsampled version of the previous layer BI times a square matrix CI. And CI again is square because we're assuming that the number of channels K is constant among each layer, and so then C maps K channels to K channels in a linear way, and that is given by a K by K matrix. All right, this is the architecture of the deep decoder. For more details, please see the deep decoder paper. But here we can talk about what are the parameters of it, right? The things that are actually optimized at inversion time. And this we'll call theta, and these include all of the C's, so the C0 up to CD-1, which are all K by K matrices. And then in the very last layer, the one that converted it to have a 3-channel output, then it's a K by 3 matrix. So then theta is also going to contain all the normalization parameters, which I won't detail. So if we asked how many parameters are there in the deep decoder, roughly speaking, they're K squared D parameters. All right, now that we have the deep decoder, let's do some interesting things with it. So the first interesting thing to observe is that the deep decoder can concisely represent images. So that means given an image, you can estimate some parameters theta where the theta corresponds to the image, where there are actually very few parameters theta relative to the number of degrees of freedom of the image. So you could solve, in this case, the L2 minimization over theta of the norm of f theta of z minus x. Remember that z was some fixed quantity in advance, and let's assume for now that it's random noise, but you can generate it in other ways as well. Now what's somewhat surprising is that the deep decoder can actually outperform wavelet thresholding at representing natural images in the case of severe compression. So what's being plotted here, each x corresponds to an image in the ImageNet dataset, and then there was the image was represented as a sum of wavelets, but only 1 over 32.3 of the wavelet count was kept, and then the image was reconstructed. There was some error that was recovered by that, and so then that's the horizontal axis, the peak signal to noise ratio under this top wavelet coefficient thresholding. So then the vertical axis shows the PSNR occurring from representing the very same image using the deep decoder. So what we see is that under high compression factors, most of the ImageNet images have higher PSNRs under the deep decoder that has an equal number of degrees of freedom as the wavelet representation. And this held in the case of high compression factors. In the case of low compression factors, then having an equal number of wavelets and deep decoder parameters, it was better to have a wavelet thresholding representation of an image. So these results are quite exciting because they show that the deep decoder can offer a concise representation of images on par and sometimes better than wavelet thresholding, which is itself the basis of modern JPEG representation technology. With the underparameterized deep decoder, another neat thing about it is that it can denoise images without early stopping. So what's shown here is a series of plots for using the deep decoder and the deep image prior to fit a noisy image, an image that isn't noisy, and then an image consisting just of pure noise with no signal. Right? So what we see for the noisy image with the red deep image prior curve is that initially the error of the image goes down and then starts to go up at a sufficiently high iteration count. So which is to say the error relative to the true noiseless image decreases and then eventually increases because at that point the deep image prior is fitting the noise in the noisy image that is being presented. So in contrast, the deep decoder, the error is going to go down and then it's going to stay down and not overfit the noise. Now the reason it doesn't overfit the noise is because it doesn't have enough parameters to represent the noise. Now in the second column here, what we see is that both the deep decoder and the deep image prior have the capability of representing the image exactly. And that's great because we need the signal we're wanting to represent to be in the range of these models, and indeed it is. And then the final plot shows for a case of just pure noise what happens versus iteration count. All right, so the question of why doesn't the deep decoder fit noise well? Well, the answer to this is simply because in the underparameterized setting, it doesn't have enough parameters to fit the noise. And this is something which theory can even be stated about. So there's theory that says that underparameterized deep decoders can't fit noise. And this is formalized by the following claim in the deep decoder paper. And that said, consider a one-layer deep decoder. So fix some input B0, which we'll say is a N0 by K matrix. Again, this is the quantity Z that we were referring to before. So also fix an upsampling operator U0 from in N by N0 matrices. So here the one-layer deep decoder is going to be some function for now. In order to be consistent with the notation of the paper, let's call it capital G of the matrices C0 and C1, and this will be ReLU of U0, B0, C0 times C1. And here, again, U0 and B0 are fixed and arbitrary matrices. Now, in this claim, we're going to assume that eta is some noise image. Right, so here, the point is that we're going to try to use the deep decoder to represent a pure noise image, and we're going to say that it can't do this. Right, so if k squared log n0 over n is less than 1 over 32, then we claim with high probability that the minimizer over all C0 and C1s of g of C0 C1 minus eta, the L2 norm of that squared, that is at least the L2 norm of eta squared times this constant that's close to 1, and it's 1 minus 20 k squared log n0 over n. Right? So what this is saying is, with high probability, if k squared is sufficiently small relative to n, then the amount of noise that is fit is quite small. Meaning the remaining amount of noise that is not fit is large, meaning that the noise was not actually representable by the deep decoder. Now, it's possible to understand the scalings of this using a rough rationale. So let's think, how many degrees of freedom does the deep decoder have? Well, roughly speaking, it has k squared degrees of freedom. In this case, we are considering a one-layer deep decoder. In a d-layer deep decoder, there'd be roughly k squared d parameters. Now, a k squared dimensional subspace of Rn is going to admit a fraction k squared over n of the noise power. So if I just fix the subspace and then generate a Gaussian noise and then project onto this k squared dimensional subspace, the square norm of that's roughly going to have k squared over n of the total square norm of the noise itself. And so this is a result from basically linear theory. And the idea of the proof of the deep decoder is that the range of G, the range of this deep decoder, lives in the union of a known number of different k squared dimensional spaces. And one can bound this number by n0 raised to the k squared. So here we have relatively few different subspaces of dimension k squared, and one can work out the mathematics to get the bound above. So in some sense, what's going on is that, right, the deep decoder is under this model, it's a piecewise linear function, right? In any given piece, you're really in this k squared dimensional linear setting, which is just like the beginning of this rationale. Now, this claim, as proven, is only stated for the one-layer deep decoder. The argument can be extended for two-layer deep decoders, but no proof is currently known for extending this to a deep decoder of an arbitrary number of layers, and this would be an area of exciting development for the field. So far we've talked about the deep image prior and the deep decoder, and now let's talk about a prior that's actually quite different and comes from a different area, and then we'll see that there can be a bit of connection, and this is going to be the deep geometric prior. So this prior is coming from the problem of surface reconstruction in 3D. So what that means is that given a set of noisy points, which we'll call xi, and these are all points that are along some surface in 3D, but they are noisy, then the goal is to estimate the surface. Right? So here's an example, a collection of points, and from those points we want to estimate the surface itself. Now, mathematically, we could represent a local patch really as a function that just maps the square in R2 into a region in R3. And we're going to try to find this function phi. So here we're going to take some collection of points vi, which live in the unit square in R2, and map them to precisely the xi's that we received. Although, I mean, I shouldn't say precisely, because we actually only want to extract the smooth surface that underlies these noisy points xi. So the process for estimating the surface is going to be as follows. So choose some vi's in the square that have the same number of points as the xi's that you have in R3. And you could, for example, choose these randomly. Then your first process may be to find the best matching between each of these vi's and the xi's. And you could do this possibly by minimizing the earth mover distance between vi and xi. Now that is, as stated, a difficult optimization problem to solve, but there are relaxations that are that make that doable, and you should see the deep geometric prior for the details of how to do that. But let's suppose now that you have a good matching between the points vi and xi. So then what we need to do is find a representation of the function phi. And here what the authors do is they represent it with a fully connected ReLU net, where here there's going to be d layers, and each layer is just going to be some matrix theta I acting on the output of the previous layer, and then having a ReLU act on that and do this d times. So what's interesting about this architecture is there's really no structure, right? It's a fully connected net, and there's in principle no real bias that is put into this net by its architecture. Once we have this representation for phi, we can then write down a minimization problem to solve, and then we might write down the natural problem, which is minimize over all these parameters theta of the sum of the square distances of the map phi applied to our points vi, and the distance from that to the xi points that were in R3 to begin with. Right? So the goal is to optimize this over theta, and what you can observe is that during the optimization, the overall shape that you're trying to reconstruct gets fit first, but then eventually the noise gets fit. And so we see we're in the same sort of circumstance as the deep image prior, so this would lead you to do early stopping. And if you do early stopping, then you'll get an estimate of the shape without fitting the noise, hopefully. Now, while that was stated in a surface reconstruction setting, we can actually apply these to images. For example, if you have an image X, right, that could be viewed as a map from the unit square in R2 to values in R3. Here, the input of this function, right, it's a position, which is to say, like, which pixel in the image are you in X and Y, and the output is in R3. Those could be the three color channels, RGB, of the image. So really, this is just an alternative way of thinking of an image, less about the image itself being a vector in n-dimensional space, where n is the number of pixels times 3. Here, this is viewing the image itself as a function, which takes position into color value. Right? So then this function itself could be estimated by a neural net, and that is a way to use a deep geometric prior for an imaging inverse problem. So we have seen a couple of varieties of unlearned nets, and so it's natural to ask, what is the prior with an unlearned net? Like, can we articulate what the net likes and what the net doesn't like? So for an underparameterized deep decoder, this may be the easiest case to discuss, but it's still fairly difficult to discuss. So here we can consider the set of all possible things that are outputable by a deep decoder. So mathematically, this could be the set of f theta of z over all theta. And remember here that z is fixed and applied to all images. So it's really just fixed once and forever. So this set, if the deep decoder is underparameterized, this is going to represent a low-dimensional manifold in Rn. And so then the prior mathematically is just that we're searching for an image which is a member of this set. Now, it's not clear exactly what the members of this set, what property those enjoy. But because of the low dimensionality, then this is only going to be able to fit low complexity signals in some particular sense, though we don't have a characterization of what that sense is exactly. Now, in the case of overparameterized problems, it's less obvious what the prior is. So here in the overparameterized nets, the rough story is that they can and do fit anything. Right? If you wait long enough and train, do the optimization for long enough, then you will fit even pure noise. But nonetheless, these overparameterized priors without learning still prefer some low complexity signals. Right? Now, it's not clear exactly what aspect of low complexity is preferred by these priors. One natural guess is that it could be something like piecewise smoothness. Another possible guess is it could be something like having a small Lipschitz constant. And so perhaps among different solutions, the overparameterized priors initially lead toward regions that are more piecewise smooth or regions that have better Lipschitz constants, and it only leaves these regions if it has to. So the key thing here is that gradient descent itself traverses these signals, these low complexity signals first, before it leaves that region in order to fit data that you have given it that is inconsistent with a low complexity signal. Right? So this answer is a bit unsatisfying for what is the nature of the prior of these unlearned methods. And this is something which, again, future work will hopefully resolve, and this would be an exciting development to the field. Another interesting question to consider with these unlearned priors is, how do they deal with smoothness and locality of images? Right? So if you were to ask someone, what is special about natural images that is not enjoyed by arbitrary images or images of static? What is the special property that we want to exploit in order to recover them from relatively little data? Right? So normally, the answer to this would be something like piecewise smoothness, or there's locality within the image. That is to say, the color values of one pixel is strongly determined and very similar to the color values of neighboring pixels, though there are also very sharp jumps in images, for example, due to occlusions. So we should see, where do all of these priors fit from this question and perspective of smoothness and locality? Now, with the deep image prior, smoothness is achieved in a variety of ways. For example, there's upsampling operators, there's convolutions of various kernel sizes, and even sometimes the input z to the deep image prior itself had smoothness properties. So what they observe for the case of in-painting, in the case of that table with the missing vase on it, was two of the channels as input. They gave values that were basically corresponded to the x and y coordinates within the image itself. So this is actually quite similar to the deep geometric prior in those channels. Now the deep decoder, the only way that it gets continuity or smoothness is through upsampling. It only had one-by-one convolutions, which have no spatial extent, and so those have no direct effect on the smoothness or locality within an image. And then finally, with the deep geometric prior, the way that it achieved smoothness was because the neural net itself was a continuous function and was applied to continuous input. So neighboring pixels give nearly equal color values because they have nearly equal inputs. And only if the neural network has put a very sharp jump between neighboring pixels are you going to have significant jumps. All right, so that reviews the basic ideas in the unlearned nets literature. And so what I want to finish with is just two papers that are out there that can be viewed as bringing ideas from unlearned nets into the world of learned nets. So the first of these papers is the image adaptive GAN. And here, the idea here is that you can use a trained GAN as a warm start for a deep image prior. And so let's go back to our figure that we had from before. We have some generative model G, which was trained. It's going to take some image-specific Z, and then some image general theta, and then output X given Z and theta. In the image adaptive GAN, what they'll do is they're going to optimize Z and theta together in an image-specific way at inversion time. So specifically, they're going to minimize Z and theta of the L2 norm of the forward map of G theta of Z minus Y squared. So this could, what this can do is it can exploit the learning of the generative model G by quickly finding the Z that gives the point in the range of G that's closest to the image that you're looking for. But one common issue with GANs in particular is that they have representation error. So which is to say, for the fixed theta that you trained the GAN G to have, there may be no value of Z that's particularly close to the image that you're desiring. But we do know that it is possible to have neural network weights that contain that image, so hence the idea of optimizing the weights of the generator itself for this image. Right? So philosophically, this is a bit different than just simply using the GAN G as a prior, because there the idea was you trained a generative model to sample from this distribution, and you're asking for the object in the range of that generative model that's as close as possible. But instead, the fact that the IA GAN is now optimizing over the parameters of that theta is really combining the worlds of the generative modeling and of these unlearned priors. Now, the final paper that I want to mention is the latent convolutional models paper. And in this paper, what they do is they use the deep image prior as an image-specific prior for the latent representations of images. And they did this in the case of a generative model like a GAN, but not actually a GAN, something called a generative latent optimization, which has a very high dimensional latent space. So they observed that the latent space was high enough dimensional that they actually needed this untrained net, this DIP, to act as a prior for what latent representation corresponds to a particular image. So, and please see the latent convolutional models paper for more information there. So what we've seen in this lecture is that there were a variety of unlearned nets out there that can be used to solve imaging and other problems such as surface reconstruction. So maybe it's worth, just as a last thought, reminding ourselves, what was learning, and in what sense are these methods unlearned? So a commonly accepted definition of learning is that it is the improvement of performance at a task upon seeing additional data. So in the case of classification, it would be if I show you more examples of the classes that you're trying to classify, then your performance at classifying them should improve. So in the models that we discussed today for these unlearned nets and untrained nets, there was no training data. And so hence there cannot be any learning. And this is a significant aspect because if you think about the practical applications of inverse problems, for example, think of something like MRI imaging. With MRI imaging, if you're a major company going to build a scanner that's going to make these images, then you're very interested in knowing whether you have to start your process by collecting possibly millions of sample images and then processing them, labeling them perhaps in some way in order to train an algorithm. If you could, you would prefer to not have to do that because it would be cheaper. And so in unlearned nets, there is no need to go out and collect a massive data set in advance. Now, of course, one would only and should only collect such a data set in advance if you gain benefits from that learning process. And so hence it's natural to think that any algorithm for solving inverse problems based on learning should actually outperform methods like the deep image prior and the deep decoder that aren't based on learning. So this is to say, unlearned methods should be a benchmark that all learned methods are judged against. Now, another final thought is the potential benefits in a clinical setting for using unlearned methods. Now, there's some excitement and hope that we've talked about before in this class that learned methods based on generative modeling could be exciting ways to minimize the amount of data needed to recover images, such as MRI images. Unfortunately, the training process involved in learning has a bit of an Achilles heel. Right? You're only as good as the training data set that you've provided. Now, you may accurately represent that training data set, but perhaps you become so good at determining what looks natural that a generative model actually hallucinates a tumor where there is none, or it hallucinates not a tumor where there is indeed one. And this could happen because they're operating a regime of relatively few measurements, and so the net might have to make a decision between data fit and naturalness, and it could say that the more natural image is the smoother one, which removed the tumor. Right? So this could output in an image which looks very pretty, but actually is clinically erroneous. Now, in contrast, a method without learning, like under severe lack of data, it's going to have problems as well, but those problems are going to manifest as not semantically meaningful artifacts. And so that means a doctor may be able to see such an artifact and identify it positively as an artifact, and hence something from which a clinical decision should not be made on. Right? So here what we see is that it may be that in some cases it's very useful to exploit the fact that unlearned methods both are less expensive to train because you don't have to actually buy the training data or acquire it somehow. And they may actually lead to higher quality images because they're less susceptible to hallucinating details.